with this lecture, we will move into a new concept, which is the idea of structural instability. So, all this while in the course, we have mostly talked about the stress and strain that develops in a structure due to an applied load. The applied load could be bending, torsion, axial load, tensile load, compressive load, and the primary concern for us was to find out the stress distribution in the cross section because of this applied load, and thereby find out the value of maximum stress. It could be direct stress or shear stress, and to check whether this stress is below the allowable limit of the stress of the strength of the material. So the maximum stress developed should have been less than the ultimate strength of the material. Otherwise, we had to redesign the entire configuration or entire structure to bring down the maximum stress that is developed below this allowable limit. So this is what we have done through the entire course till date. But today we are going to move into an entirely new topic, which is called the structural instability. Okay, so there are various forms of structural instability. We will not go into that. What we will be mostly concerned with in this course is the buckling of a structure. So all of y'all must have heard about the term buckling. Okay, as I mean, not only from structural perspective as well as from general vocabulary. So buckling means that a structure is going to buckle or bow due to the application of compressive load. That's a layman's kind of definition of buckling. Now, since aircraft structure comprises of thin plates and shells, okay, like in a semi-monocoque structure, and reinforcing members like stringers and longeron, which are slender beam-like structure, they are very vulnerable to buckling. So any of this portion of a semi-monocoque structure of an aircraft, when experiences a compressive force, it 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 has this tendency to buckle or bow because of this compressive force that is being applied. This is more because we deal with thin structure in aircraft components and long slender beams in aircraft component, and that's why buckling is a persistent problem or persistent issue that one has to keep in mind while designing aircraft structure. So what we will do is that in this course we will start with basic fundamental column buckling and then move into buckling of plates, and then we will go into more complicated forms of buckling which are called torsion flexural buckling. So leaving those aside, let us first start with what is meant by buckling. So the theory of column buckling was first proposed by Euler. Also called as the Euler buckling of column. So this is also called was first proposed by Euler in 1744. Okay, and practically the same theory is still existing, and that is the primary theory of analyzing buckling in slender column. So what does it happen? So if I take a column, a slender column, If I take a slender column and apply compressive load P, okay, so this is P, which is a compressive load, and we keep increasing this P. So we keep increasing this P. So this is P that is increasing. Okay. So when P reaches a critical value, then this column buckles or undergoes large deformation in undetermined direction. Okay. And that is called buckling. So let me just put it into words. So what happens is that if an increasing load axial compressive load is applied to a slender column, then there is a value of the load which is called the critical value at which the column will suddenly bow or buckle in some undetermined direction. Okay, unpredetermined direction. I shouldn't call it undetermined. Okay, so let us revisit what I have written and let us see the important point. So it has to be an axial compressive load. Okay, it should be applied to a slender column. So buckling usually happens with slender column, not very stout kind of column. Okay, and the at a at a certain value of load, this is called the critical load. This is called the critical load. Okay, the column will suddenly bow or buckle. So this is going to produce a large deformation. Okay, and since it is a large deformation, this will be associated with large strain and stress, and of course it is going to fail. Okay, and in unpredetermined direction, that is, you don't know whether it is going to buckle in this direction, whether it is going to buckle in this direction, whether it is going to buckle in this form, or it is going to it is going to buckle in this form. These things are completely undetermined previously. You cannot keep them determined. Okay, and this whole thing, this critical load is most often much below the failure load, compressive failure load. Okay, even if we forget about buckling, if we have a column and if we give an increasing compressive load, axial compressive load, at certain point the column is going to fail because of the compressive failure. The compressive stress that will develop will be more than the ultimate strength of the material, and thereby it's going to crush, or it's going to fail under compressive failure. But when this column is a slender column and there is a critical load, which load is most often much below this failure compressive load, the column will experience a buckling, and this buckling is going to be in any unpredetermined direction and is going to be of large deflection. So this large deflection is going to give rise to large strain, and thereby large stress, and thereby it's going to fail at a load, or which we call the critical load, which is much below the actual compressive failure load. Okay, so this in a very layman's way is what is meant by buckling. So when does this buckling happen? This buckling usually happens when this buckling usually happens is caused by caused by geometrical and or material imperfection of the column and its load, and or its load. Okay, let me try to describe this. So this buckling phenomena that you can observe in a slender column is usually caused because of some geometric or material imperfection of the column, or the imperfection or unsymmetry of the applied load. Okay, so a column is bound to experience some imperfection in the geometry as well as material, and or in the material, and this imperfection is rather unavoidable, right? Because of manufacturing process, because of the deployment condition, because of misalignment in the boundary condition, the boundary restraint. So this kind of imperfections are rather unavoidable. However perfectly you build a column, because of the human factor involved in it, you cannot avoid the imperfections that are going to be there, both in geometry as well as in the material property. There could be some material inhomogeneity, I mean lack of uniform dispersion of material, and that is what gives rise to this kind of buckling. So theoretically, ideally, if we can consider that the structure is perfect, there is absolutely no imperfection, and the load is perfectly aligned with the neutral, with the centroidal axis or the neutral axis, then perhaps we can imagine that there is not going to be any buckling. Okay, but this usually does not happen, and this is usually not the scenario, that we cannot achieve a perfect column or perfect loading system, and therefore buckling is an important failure mechanism that is experienced particularly by aircraft structure. Unlike many other structures, civil and mechanical structure, aircraft structure, being thin and slender, are very much susceptible to failure by buckling. Okay, so with this, let us go into a much more theoretical understanding of buckling. Okay, so let us try to understand what is meant by buckling. Okay, so let me take a column. Okay, and let us consider. So this is a perfect column. So consider a perfect column. And P is applied perfectly along the centroidal axis, and there is perfect symmetry that is there. So if this is the condition, that we have considered, buckling will not happen. Okay, whatever large the value of P is. Okay, so if I have such a perfect column and I keep applying an axial compressive load perfectly along the centroidal axis, so that there is absolute symmetry in the whole process, then whatever, if we keep and the column is slender, I have no issue with that. So perfect slender column, and I keep increasing P, there is not going to be any buckling, however large P is. Okay, so what is going to happen? This entire structure, this column is going to fail because of compressive failure. It is going to get crushed, and at certain high value of P, the compressive stress will cross the ultimate compressive strength of the material, and the column is going to get crushed, but no buckling is going to happen. So you please note this. So no buckling is going to happen. Now, to, to, to theoretically understand buckling, what we are going to do is that we are going to apply a side wave force F. Okay, and this side wave force is going to, or this lateral force, okay, is going to buckle the column. Sorry for the term buckle. It's not buckle. So it is going to displace the column by a small amount, say V. Okay. So V is a small lateral displacement of the column. Displacement due to F, not buckling. Huh? So I'm sorry I said buckling. So don't, it is not buckling. This is just the lateral displacement because of the applied force P. Okay. So now if we have, let us consider the three cases. Okay. So the first case is when P is less than a critical value, which we call P critical. So we call this as critical load. If P is less than a critical value, P critical, then the column will return to the undeformed position when the force F is removed. Okay. So the column is going to return to the undeformed position when F is removed. Okay, so that is first case, and this case is called the case of stable equilibrium. You of course know what is meant by stable equilibrium. So this is the case of stable equilibrium. Now let us go to the second case. The second case is when P is going to be equal to P critical. Okay, so when P is going to be equal to P critical, the column is going to stay in the deformed form or position when F is removed, but there is not going to be any further deformation. Okay, so the column is or will remain in the deformed position when F is removed. Okay, and this is the neutral equilibrium. Okay, and the third case is when P is greater than P critical. When P is greater than P critical, then the column will deform further even when F is removed, and it goes into an unstable condition. Okay, so the column will deform further when F is removed and will be in unstable condition. Okay, and therefore this is called the unstable equilibrium condition. Okay, so this is what is going to happen at the different values of P. Okay, so let us take up the job of finding out P critical. Okay, so let us see how to find out the critical load P. Okay, so that is going to be our next job. Okay, so let us try to do this. So let us consider a pin column. Okay, of length L, so length will L. Okay, and let me draw the axis. So this is the Z axis, the lengthwise axis. This is Y axis, and this is the X axis. Okay, so two loads, axial compressive load P and P is going to act here. So let us consider this to be a perfect column. So in order to buckling to get induced, let us consider that this is having an initial small deformation which is defined by small v, which is a function of z. Okay, so now, if I try to write down the equilibrium equation, so let me take a small portion of the okay. So let us take a small portion of the column and just do the. So this is P. This is going to be P. Okay, and this is going to be the moment M. Okay, so from moment balance equation, what do we get? If we do a moment balance here, I am saying that M plus P into Vz is going to be equal to 0. Okay. So in place of Vz, in place of moment, moment can always be written as EI d2v by dz square. Okay, so therefore this equation can be written as ei d2v by dz square plus pvz is going to be equal to 0. So this further can be simplified as d2v by dz square plus p by ei into v is equal to 0. So this part, let me call this as mu square. Therefore, this whole equation can be written as okay. So this is the equation in terms of v. So now if I try to solve v, the solution of vz is going to be a cos mu z plus b sin mu z. Okay, so a and b are unknown, so let us apply the boundary conditions on the column. So if we apply the boundary condition, so what are the boundary condition? At z equals to 0, v is equal to 0. If we apply this boundary condition, then our a goes to 0. Okay, and the next boundary condition is at z equals to L, again v is equal to 0 because it's a pin-pin condition, and that is going to give us the solution as b sin mu L is equal to 0. Now b cannot be equal to 0, okay, for non-trivial solution. If a is already 0, if b is equal to 0, then vz is 0, which is a trivial solution. So b cannot be equal to 0 for non-trivial solution. Okay. So the only possibility is therefore sin mu L is going to be 0. Now sin mu L is going to be 0 when mu into L is going to be n into pi. Okay, so n is going to be 1, 2, right? Except 0, because 0 is also going to give me a trivial solution. So except 0, n could be any integer value. So if I do that, then my mu square is going to be n square pi square by L square. Okay, which gives me p is going to be n square pi square L square by ei. Okay, so that is going to be the value of the p, the solution of this. Okay, so when p is going to be equal to of this form n square pi square by L square, only then this is the system that we have drawn, a perfect column with an axial load and initial small displacement of lateral displacement of b is going to be a solution only when my p is going to be n square pi square ei by L square, and this is a stable equilibrium, so my p is actually equal to p critical. Okay, because this is a stable equilibrium problem that we have solved. Okay, so therefore for a pin-pin column, what we can say, for a pin-pin column, P critical or critical buckling load is going to be pi square EI by L square. Then it is going to be 4 pi square EI by L square, and so on. So it is going to be 9 pi square EI by L square. Okay, now this is called the first buckling, first critical load. So first critical load. This is of course the second critical load. And this is the third critical load, and so on, of course. Okay, now if I have the column, so what is going to happen if I have the pin column and I give P equals to pi square EI by L square. P is going to be pi square EI by L square. Then this column is going to buckle in this form. This is undetermined. I mean, could be any value but stable. So this could be any value but stable. Okay, right? It could be any value in this direction or this direction. So this is called the first buckling mode. Okay, and then if I take the same column and I apply the force P, which is 4 pi square EI by L square, and this P is also 4 pi square EI by L square, then the column is going to be formed in this form. Okay, or this form. I don't know any of this. Okay, so this is the second buckling mode. Okay, and this value is again undetermined. We cannot say for definitely what is going to be this value, but it is going to be stable, and so on. The third buckling mode is going to be something like this. Something like this. Okay, so this is going to be the third buckling, right? So if we try to write down the expression, so for the first buckling mode, Vz is going to be some constant A1 or B1 if you want to call it. It is going to be B1 into sine pi Z by L. And for the second buckling mode, this is Vz, which is B2 into sine 2 pi Z by L. So this B1 and B2 are constant which can take any value. Okay, right? So this kind of analysis, if you can appreciate, is a eigenvalue kind of analysis. Okay, and therefore these solutions are called the eigenvalue solution, and the shape are actually the eigenfunctions. Okay, So the pre-critical value, which is pi square EI by L square, is the eigenvalue of the solution, and this is the eigenfunction. Okay. Now, if I try to plot this entire process in a certain way, and then I can actually plot it. This figure is a nice depiction of how buckling is going to happen. Okay, so let us call this as Vz. This is Vz, and this is P, the applied axial compressive load. And this is the deformation. Okay. Now, if we keep on increasing the load, there is going to be no deformation that is happening till a point where we reach P as P critical, which is pi square EI by L square. Now, at this point, there are three things that can happen. So, if we give a perturbation, any perturbation, it can move in this direction. It can also move in this direction. And if there is no perturbation, it will move in this direction. So, this point is also called the bifurcation point. Okay, and if there is no perturbation, this will keep on going, and then at another point, let me just erase this off. Okay, so now if I don't give any perturbation and keep on increasing my P, then at a point where P is going to be equal to P critical 2, that is 4 pi square EI by L square, again that is another bifurcation point. Here also the deformation can happen in this direction, the deformation can happen in this direction, or if there is no perturbation, it will move further. Okay, so this shows that how the column will behave if we keep on increasing the load, and at different critical values of the applied load, how is the column expected to behave. Okay, so with this we will end this lecture. In the next lecture we will try to understand columns with different boundary conditions, as well as column under different other forms of loading. Till then, thank you.